Hello again. So in the last video we talked about this circuit right here, which is built on these four breadboards. So yeah, in the last video we demonstrated uh, this circuit basically going through a program. So basically the circuit is just the clock, the program counter, the ROM, and the instruction decoder. So what this can do is it could step through the instructions of a program, and that's about it. Uh, Problem is, in order to actually build a computer, we have to do more than that. We actually have to execute upon those instructions. And a big part of being able to do that is having an ALU, or an arithmetic logic unit. The arithmetic logic unit in the computer is what actually does the computations. If you have to add two numbers together, subtract two numbers, do bitwise operations, whatever, it always involves the ALU to some extent. And that's what I have built right here. So on these breadboards is the ALU which I have built. And what I'm going to do is eventually I'm going to connect these two together, and that's going to be done using this other circuitry right here, which I haven't connected yet. Yeah, so these are just registers which are going to go into the ALU, registers that are going to come out of the ALU, and then there's some more control circuitry as well as the RAM. And once I have all that connected, I could actually build a computer. But yeah, what I have right here is just the ALU, which is just a combinational logic circuit. And this is a 7-function ALU, so basically what it can do is it could add, subtract, pass through the two inputs, and it could do bitwise and, or, and invert of an input. So yeah, this is basically the entire circuit right here for the ALU. Just what we have right here, we have a 4-bit adder, some exclusive OR gates, so we could actually turn the adder into a subtractor when we need to. Then we have AND gates, OR gates, and inverters. And then we have some AND gates right here, which basically allows to enable which function we want to see on the output. And then these all go to a bunch of OR gates and are ORed together, and the output is displayed on these LEDs for now. So here's the actual schematic which I have, just to show it in greater clarity. The ALU has two inputs, A and B. These are both 4-bit inputs, so 4 bits of A and 4 bits of B. And then we have our 4-bit output, which is F. And in addition to that, we could actually select which function we want to do. So it's a 7-function 4-bit ALU. So our functions are to add, subtract, pass through input A. So that means that F is going to just be A. And then we could pass through B. So F will be B. And then we could do bitwise AND between A and B, bitwise OR between A and B, and we could invert A as well if we need to. Of course, these logic gates kind of explains it better. So just for the add and subtract, we have our 4-bit adder, which, as I had explained, is this IC right here. I guess it really doesn't matter, they're all covered in wires. But yeah, so we have a 4-bit adder, and obviously that could be used to add. But as well, we might want to be able to subtract. So in order to turn an adder into a subtractor, the number that you want to subtract has to be turned into its 2's complement form. And in order to make a 2's complement number, you have to invert all the bits and add 1. So basically, if we want to subtract, we're going to have a carry in, so this is going to be the add 1 part. And then the thing with exclusive OR gates is you can use them as a conditional inverter. So we invert all the inputs for B. So what this will allow us to do is, if we want to add, we could do A plus B. If we want to subtract, we could do A minus B. there is no b minus a, so just whatever. That's just how it works. One thing that we have to do is in order to actually select which function we want to do, all the outputs go through these AND gates. Also, there's an OR gate right here because basically the outputs of the adder have to be passed through these AND gates, whether we're doing addition or subtraction. But if we are doing subtraction, we're also going to have to do this business with the exclusive OR gates and the carry in. But if we're just doing addition, then these remain 0, so we're just adding, but we still pass the outputs of this through these AND gates, which will then flow through these OR gates, which ORs all of the different functions, and that passes through F. So that will give us A plus B or A minus B. Also, we have our pass-throughs to pass through A or pass through B. With the way this computer is going to work is that there are registers up here and there's going to be registers up here. And sometimes for some instructions on this computer, like store or load or input, we might have to just pass data through the ALU without doing anything to it, just to move it from one register to another. So that is accomplished via a pass-through function, which basically just means everything in A just goes straight to the AND gates, and if pass-through A is high, then that means that all this data gets passed through. So we can pass it through with AND gates because it basically lets us turn on and off the output. And of course, that also goes through the OR gates to F. So OR is everything, so if any of them is high, it'll go through to F. So once again, that is accomplished by having all of these functions disabled except for the one that we're actually doing. And then we have a pass-through B. It's the same as this except for B. So if pass-through A is high, or if pass-through B is high, all the outputs of B are going to go through these AND gates. They're going to go through the OR gates into F. And then, of course, we have our bitwise AND for A and B. So we're going to AND these two, and then the enable pin will go to these AND gates, and then it'll go through the OR gates into F. Same thing for a bitwise OR. So we're going to OR A and B, and then they go through the AND gates to the OR gates to F. And we also have not A, so same thing, it goes inverts and then AND gates, OR gates to F. This ALU has every function that I need in order to implement all the instructions for this computer. This computer has like 12 different instructions, but a lot of them are just going to be passing through A and B, and of course we have all the rest of them. So let's actually demonstrate this ALU just to show that it works. And we can do that by turning on our power supply. And now it is on, but of course we're not going to see on anything on these LEDs because we have to select the function that we want to do. So we have two inputs. We have A and B. These are 4-bit inputs, and they're chosen by here. So this is A and this is B for the blue, which comes down to here. So if you could see it from the breadboard, A is going to be 8 plus 4. So A is going to be 12 and B is 2. That just for examples, they should be able to be anything. And then we have our function selector. So once again, we have 7 different functions. They go add, subtract, pass through A, pass through B, A and B, A or B, invert A. So let's just say, let's add it. So what we're going to do is we're going to add 12 plus 2, which should be 14. So yeah, 12 plus 2 should be 14. Yeah, we just had to tap this. The breadboard connections are not very good, but just to show it again, let's say 12 plus 2 is 14. Yeah, so some of these connections are not very good. That just has to do with it being on the breadboard. So let's see what 12 minus 2 is. So 12 minus 2 should be 10. So let's see if that's correct. So we have 8 plus 2 is 10. All right. So that looks good so far. Now let's pass through A. So 8 plus 4 is 12. That looks good. And let's try to pass through B. Let's see what we get for this. So B is 2. Yeah, B is 2. Works. So let's see if we could do A and B. That A and B should be 0 because no overlapping bits. So you can see we're doing it right now. A and B is 0. Let's see if we could do A or B. It should be 14. These two are coming from A, and this one is coming from B. So A or B is 14. That makes sense. And let's see, invert A. So once again, A is 12. So A is these two. So invert A should be these two, which is 3. With bitwise operators, it really doesn't make very much sense if we treat it like a number. We just treat it as a series of bits. Oh yeah, look, invert A is 3. So yeah, that's that is just a basic demonstration of the ALU. Let's try to maybe do another one. Let's maybe change one of these so we could show a different number. So instead of 2, B is going to be 5. Yeah. Now B is going to be 5 and A is still going to be 12. So this I think would actually overflow. So 12 plus 5, so that's 15, 16, 17. Yeah, so now that we've changed B to 5 and A is still 12, 12 plus 5 is 17. So what's invisible here is that right now we're going to actually be doing a carry out. So we could have basically another LED here that represents 16, and this is going to be 17. So that's an example of an overflow. But that one bit is correct. So let's do 12 minus 5, which should give us 7. Yeah, 12 minus 5 is 7. Of course, we could pass through A is 12, B is 5, do a bitwise and between them. So yeah, 12 is these two, 5 is these two, so this is the one in common. So that makes sense. And we could do a bitwise OR. So bitwise OR, once again, 12 is these two, 5 is these two. So every LED that's involved in either A or B is on. You could do an invert A, which should be the same as the last time. It's going to be 3. Alright, so this ALU seems to work pretty good. So now all I have to do is integrate it with the rest of the computer. So the instructions given by this part should actually be able to determine the function of the ALU, and then we could use the sub counter count to actually pass through information to 2 different registers. And that should be a working computer system which should be able to execute a basic program. And then we have made a programmable computer out of some pretty basic logic gates, really. So yeah, thank you for watching this video, and I'll see you next time.